Any questions?
Her and I got the same numbers, and I got 4s and she got 10s.
Okay, just, while you're doing the lab, I'll take a look at that again. Other questions? Hi?
Could you do a projectile motion problem, like, number 8 on the master set?
Pretty much version of it.
So that's the egg, launch horizontally, okay.
I gave you horizontal displacement,
You did.
and I asked what's the initial speed?
Initial speed, and then fired straight up, height.
Okay.
All right, so I have something being shot off to the right. Or
Horizontally.
I'm just making it to the right, there we go.
And as soon as it is released, it's going to start to fall. And so if I know the initial height and distance, I know that if I take an object and I drop it at the same time I launch this one, that they will hit the ground at the same time. And we can, in theory, demonstrate this. Spins and, here we go. So as I swing the meter stick, this one is going to be moving faster than this one will, because it's being pushed farther. And it's going to have to sort of trust, if you can't see when they land, perhaps listen for it. They hit about the same time?
Yeah.
So that's the principle that's involved here, that if I know the initial height, I can figure out how much time it's in the air. If I know the distance that goes out that way, I know the horizontal. Because the acceleration, actually, while it's in the air, what are all the forces acting on it?
Down.
Weight.
Oh.
Okay. You had half of it. All right, so we have this weight acting down. So the direction of acceleration is down, which means the change in velocity is,
Down.
yep. See, you just answered too early. So there's no change in the horizontal piece of it, because all the change is vertical. All right, so let's give some numbers here. Let's make this 2 meters and make this 7 meters. So the first part of it is, how long does it take to fall? Well, this is a chapter 3 problem. We have that displacement is 1/2 AT squared. Or let's do the math brainwashing thing. Delta Y. So, what's the acceleration as it falls?
Oh, the acceleration is acceleration due to gravity, so the
Yeah, all right. Now the distance it's going to fall is 2 meters, so 2 is equal to 1/2 times 9.8 times t squared. There's several ways of going about it, but 2 is equal to 4.9 times t squared, that's 1/2 of 9.8. Now what?
Divide was tied by 4.9.
Yep. And so we have t squared on the right, and then whatever, it's gonna be somewhere a little bit more than 0.4.
0.40816.
1/6. And therefore, the time that's in the air,
Square root is 0.6388.
6388.
Uh-huh. Seconds.
Like you mean it?
Seconds.
Yes, there we go. Yeah, it's time. So I know it's in the air that for 0.6388 seconds, I know it's gonna go 7 meters horizontally, and so the initial speed, well, that's distance over time. My initial speed is the same, the horizontal component's the same the entire time. And so that ends up being 7 meters over 0.6388 seconds. And somewhere around 10.
Yeah, 10.958 meters per second.
All right, so that's the initial speed. And I believe the second part is, if you throw it at that initial speed straight up, how high does it go?
Isn't that the average speed? Displacement over time?
Because horizontally, the velocity is tangent to the curve the entire time. So at this point, the velocity is in that direction. If we break that up into its parts, there's a horizontal piece and a vertical piece. The horizontal piece here is the same the entire trip. It will not change. Even when it's down here, the horizontal piece still should be the same length as it was all the other times. It's the vertical piece that just keeps getting longer and longer. So because I'm plugging in the horizontal displacement here, I'm getting the horizontal velocity, or horizontal
Is the-
component, which is initially it was thrown horizontally.
I think that might be where. I didn't realize we could assume that.
Yeah. Do you want me to do the example of the second part? So we can do the second part. We have. Really? So I have this object being thrown up at 10.958 meters per second. And the question is, how high up does it go? And there are a couple ways of dealing with this. We could do conservation of energy, because once it's released, the only force acting on it is the force due to gravity, or weight. It's acting downwards. And that's conservative force. So if I just make h is equal to 0 at the beginning, h equals 0.
Which the problem actually tells you to do. It says from the point of the launcher.
Okay. So since energy is conserved, if I make h is equal to 0 here, my potential energy is 0, so it's my initial kinetic plus my initial potential, which is going to be 0, is equal to my final kinetic plus my final potential. Well, I know that's 0. If it's not 0, it's still moving, and I want to figure out how, at the peak, and at the peak it stops. So I'm going to spoil it for you. I know you were probably aching to shout it out, but I probably did not give a mass.
You did not.
Okay. This is parallel of a master set problem. If I don't give you the mass, it either means you don't need it, or I made a mistake. You don't need it. So if you don't need it, in other words, it can be anything you want it to be. You can make up a number if you want, just not 0. Or mathematically, it can cancel out. Or you let mass equal to 1 kilogram. So it's just, we can do it that way, that's effectively the same thing. So we end up with 1/2 times 10.958 meters per second squared is equal to 1 times 9.8 meters per second squared times HF. And so my final height would have, so it's probably about 120, about 60, about 6 meters.
That number, like 5.479, and if it's squared, will be 30.019.
Wait. Did you square it first?
Without square, it's 5.479. And if I
Oh, the final answer.
it's 30.01.
Yeah, there's a problem here somewhere.
Like I'm talking only about this.
Oh, you multiplied by 1/2 first and then squared it?
Uh-huh.
Yeah, the problem is that the half, if you multiply by 1/2 first and then square it, you're squaring the half.
Got it. It will be 60.03888.
6.038.
Oh, 60.
60. Okay, that's this side over here. That's 60.0388888.
Yeah.
That's equal to 9.8 times HF.
And now this. And if we divide it by 9.8, it will be 6.1264.
1264. Units?
Units.
Yes?
Just super quickly, I know, I'm sure I'm gonna ask you this every time we do one of these problems, but the reason why it doesn't matter what the mass is because there's mass on both sides, which means that they functionally cancel out.
Correct.
I'm sure I've asked you that 3 times, I'm sure I'm gonna ask you 3
That's okay.
I just wanna make sure that I have it right in my mind.
You are not anywhere close to the record for the same question being asked by the same student.
And we're ignoring the 2 meters because it's just asking where the body launched, the height where it launched.
Yeah, because part 1, or part A, the thing is thrown horizontally, and part B, it's thrown vertically, so that 2 meters is not part of this question.
And also on the master set, it says, give me the height from the point at which the ball leaves the launcher, which means the
Right.
top of the launcher is, so how far will you get from that?
Yes.
So you don't add to the ground.
Yeah, occasionally I'll do, it's thrown from 1 meter, like launch, 1 meter above the ground. How far above the ground was it? And then you have to remember to add that 1 back in. But not in this case. Emily, do you have a question or just?
No.
Okay.
And the 9.8, does that indicate down is positive? Because it's positive?
When you're dealing with energy, G, well, actually, G is always a positive number unless you're dealing with anti-gravity. But G is a positive number. Now, the acceleration might be in the negative direction. But one thing about dealing with energy is it's not effective. It's a scalar.
Oh,
But also, when you're dealing with height, it's sort of built into it that you're assuming that the gravitational pull is downwards, and that's built into it already. Other questions? Okay. I was going to move on to thermodynamics. Chapter 50. Just make life a little bit simpler later on. Stop and restart.